The idea is that I will try to convince you that indeed these kind of heterostructures are important, and we'll try to understand the basic physics because of this spin physics of these interfaces. In the process, I will introduce you with two of the techniques which we employ to understand this heterostructures, which is ferromagnetic resonance and hard X-ray photo emission spectroscopy, because the idea is that we need to correlate the electronic structure with the spin dynamics to understand the interface physics of these ferromagnetic and non-magnetic systems. And I will do so by using these two of these our results, which you can also read in these publications. So as I told you, so what is the reason we are interested in these heterostructures? The answer is very simple. We want to understand the physics of magnetic switches. And what we mean by a magnetic switch, it's an off-on state which you create by having a structure of a two magnetic material spaced by an oxide, which are when in a parallel alignment gives you a low resistive state, and when they're in opposite alignment it gives you a high resistive state. So that's a 0, 1, and then you have the whole machine you can create. But the question is how you can switch between this parallel to anti-parallel alignment and how fast you can do it. So currently we are in a gigahertz device regime, right? So we have, if you buy a computer, if you buy a laptop, you are buying 2.4 gigahertz and stuff like that. So the idea is, can we be faster? That's the question. And the second question is, can we do it with a low power or low energy? So that's the other question that concerns us. And of course, associated with it is a lot of physics, and that's what we want to delve into. So just to briefly give you an idea, and I hope there are not many experts around, and pretty much they are, but still, please pardon me. So I will briefly like to introduce you how we conventionally do it, and you have it in your devices currently, is that you drive a charge current through a reference magnetic layer which spin polarizes this charge current, spin polarized current, which then trips the magnetic direction of this free magnetic layer. Now, this process has certain problems. Firstly, you have to, you keep on driving the current through this whole device structure. That means it can become bad after a certain use, maybe a million times use. That's why you need to buy a new MRAM or whatever. So that's the problem of, a lot of power, a lot of redundancy issues and all things come up. It also generates a lot of heat current, so there's heat dissipation. So of course we want to go out of it. And the solution for it is to go towards spin orbit torque heterostructures. So the idea is that how we switch this, so to say, this free magnetic layer. And the concept here is this, that if you keep this free magnetic layer on top of some non-magnetic metal, in which if you drive a charge current, it can create a spin polarized current, and which can diffuse into this neighboring free layer and switch the magnetic direction of the free magnetic layer in the process. So the advantage is you don't need to drive the current all through the structure. So you don't have redundancy issues, you don't have high heat power dissipation and stuff like that. So clearly this can be done as it's understood with non-magnetic materials which have got large spin orbit coupling. That's why the term spin orbit torque and things come in. So I will just briefly get into a little bit of physics of it because we needed some terms during my presentation. And what happens in the process is that when you drive this, when you diffuse the spin polarized current, the spin polarized current puts some torque on the magnetization direction of this free layer, and how quickly this free layer responds to this magnetization switching depends on the term called magnetic damping. So a lower magnetic damping is advantageous. So whatever physics or whatever electronic structure designing and physical structure designing we want to do should help us to tune the magnetic damping parameter. That's the crux of the matter. Of course, there's little bit more physics behind it. So when you bring two, a ferromagnet and non-magnet together close by, what you are essentially doing is you are aligning their Fermi level. And in the process, when you drive a charge current through it, you create something called spin accumulation, and which itself creates some spin transfer torque. And associated with it is the inverse phenomena that you would expect, and this is what is called a reciprocal effect. Now, if you think other way around, I'm not driving the current. If you have a ferromagnet which has got some spin precision happening, and as it sees the interface with a non-magnet, it can transfer its transverse angular momentum inside this non-magnetic layer, and it can induce a pure spin current. So this is not a charge current, but a pure spin current, and this is what is called spin pumping. And this spin pumping also has got a kind of a relation which is in the nature of torque that I've shown you. So it essentially adds you an additional layer of magnetic damping. So to get into my results part, what is more important for you to think is that if I'm able to understand the spin dynamics at this interface and correlate its electronic structure and its physical structure, how it defines this magnetic damping, and also the spin mixing conductance, means the transparency with which the spin can flow from this side to that side, we can design efficient devices. And that's the reason we want to study these interfaces, and that's why it's very important. Yeah. So yeah, thank you. That's kind of nice. So okay, so it's 5 minutes into. Okay, so great. That's comfortable. So yeah, so so the idea is that we want to understand what is the Can you put it around? Yeah. It's fine. Yeah. So what we do is that we do want to understand what happens if there's and of course these are things that you talk about device, you are talking about dimensions which are very small. So if there is any effect of quantization on the spin dynamics, and that's what we want to understand. So what we did is that the first question we wanted to address is that what happens if we try to tune the thickness of these ferromagnetic films that is in contact with the non-magnetic layer. Can we see some effect of spin? Can we see some effect on its spin dynamics in terms of magnetic damping? And the question that we were asking was that in conventional understanding, if you go from a thin film to a bulk limit, the magnetic damping is expected to exponentially go to its bulk limit. But there are theoretical predictions that say that if you reduce the dimension, then you are expected to see these oscillations, and these have not been seen. So what we did is that we prepared such samples where we have cobalt iron.
So
yeah, thank you. So we have cobalt iron as ferromagnet, and we have tantalum, which is this high SOC non-magnetic material. Okay, and what we did is that please don't get bothered by this very busy graph. What is important is that we took this sample, we put it into a FMR spectrometer. What this FMR spectrometer allows you is to apply RF magnetic field at gigahertz frequency, which is in transverse orientation with the static magnetic field. And what we measure is a response function of this, or in the words, we measure the susceptibility, which allows us to drain out or derive certain parameters like magnetic damping and stuff like that. Okay, this is what ferromagnetic damping ferromagnetic resonance does. So that's what we did, and the result was very interesting. So as we reduce, so this clearly showed that we had a very good control of thickness of the ferromagnetic layer with respect to the non-magnetic layer. And as we tuned the thickness we could clearly see that we start seeing kind of oscillations happening in the magnetic damping. And as we go beyond a higher to the higher thickness, we get into a kind of bulk ferromagnetic limit, bulk magnetic damping limit. So the question was why? And to address this, clearly we had to understand the electronic structure variation, what was happening with change of thickness. So to do this, we did something called hard X-ray photon emission spectroscopy. And the advantage of this method is that you use X-ray photon, which is of much higher energy. What it in turn allows you is that it allows you a much higher penetration depth, which allows you a much higher penetration depth. That means you can study the buried layer interfaces, and that's why we went to do hard X-ray photon emission, and we shine a high X-ray photon with high energy, and that leads to photon emission of an electron. We measure the various parameters of this electron, which allows us to understand what is the, or rather learn about what is the value of binding energy of the electron inside the material. But there's a very advantageous thing that happens in this photon emission process, which people forget mostly, that it's not an adiabatic process, it's an instantaneous measurement, which means you also get information of excited states or excitations. And that's what we also were very much keen into looking at. So we looked at this iron 2p, for example, and you can see it's not a sharp peak, or rather not a kind of a Gaussian peak, but rather it has got a tailing structure. This tailing structure is very interesting, especially in metals, because you can think in terms of like when you have photon emission happening from iron core level, as the electron goes off from this whole thing, it can lead to infinitesimal excitation near the Fermi level. Therefore, the photoemitted electron can start losing its energy, and you can start getting this tailing happening because you don't have a Gaussian kind of structure. Importantly, what it tells is that though this is a core level spectra, it gives you information of kind of phase space that you have near the Fermi level. So that's very interesting. So you get much more information. So what we additionally did is that we did not only, we employed circularly polarized X-ray photons. What it allowed us is to do some dichroic measurement, and that dichroic measurement leads to such kind of, of course, dichroism. You can measure, and this dichroism is kind of a fingerprint of what kind of spin polarization you have at the Fermi level of the ferromagnetic layer itself. So it's not really a true measure of spin polarization, but it appears because you have an exchange interaction between the spin polarized valence band with the core level as a final state effect. So you see this dichroism, but definitely it gives you more information about the Fermi level spin polarized structure. So what we found, so when we looked at this first minima, we saw that we have, of course, this kind of iron 2p peak, but we also have within the tailing some kind of splitting happening. And this splitting happened with all this splitting in this, kind of, so to say, near Fermi level or Fermi level with the unoccupied state structure. There you have spin splitting that is appearing for all the minima place. But when you look at the maxima, there is no such splitting that appears here. And this is true for all these points. So what it implied was that when we were at the minima of this magnetic damping, there was no, there was spins, it's not easy for electron to scatter from one state to another state, because it's kind of tries to preserve, it's more energetically, it's energy unfavorable for electron to jump from this state to that state. So it's kind of a spin conserved scattering that it happens. So there's one channel less in case of magnetic damping minimas, while it is higher in case of maximas because you have spin mixing possible. So this was first such observation that we can clearly see that going from a minima to maxima, the structure of spin scattering changes, and just because of quantization, how we squeeze the thin film thickness. Just to give you a phenological picture, which I like to put in here, is that you can think like this. So you have a ferromagnetic layer which is having its spin precising in a coherent motion. So as this angle changes, your energy phase space near the Fermi level also changes. So you can have a standard scattering where you have so-called spin conserving interband scattering happening. In another case, you can have a scattering wherein you can have cases where you can create spin dependent intraband scattering, because you can clearly see at some point at certain angle you might reach a space where you have this overlap happening. So this is exactly leading to overall magnetic damping picture wherein you have both kind of scatterings possible. So we put in all these pictures together now and try to understand what's happening here. So as you reduce the thickness of cobalt iron film, what we are doing is that we have having a progressive movement of the various energy bands across the Fermi level, and at some point you are having such a band structure which is promoting spin dependent scattering. In another case it is spin conserving scattering, and that's what we had clearly seen in this whole thing, and this was kind of first demonstration of such kind of quantization effect. So it was really a very interesting thing, because this community, though it has grown quite a bit, but this kind of electronic structure quantization effect has not been seen before. So I have talked about the fact that we are talking about this magnetic layer, and we are talking about the thickness of this layer. The second part talks about what happens if we change the non-magnetic layer itself. And of course, there is a lot of studies going on, and one of such studies, this which I really like, is wherein people have changed the underlying non-magnetic layer and try to understand what happens in terms of spin dynamics, how the magnetic damping is changing, how the how fast the spin chemical potential is changing, and things like that. So what we did is that we took this cobalt iron boron ferromagnetic film, and we had different underlayer material, and this time we had tantalum, copper, platinum, tungsten. The idea was to have systems which have low spin orbit coupling, and then we have systems which have got high spin orbit coupling, and see how this electronic structure wise affects the spin dynamics itself. So the spin dynamics measurements were already done by another group of Professor Berman, and they have seen that that if you go from tungsten to copper, which is a low SOC material and a high SOC material, the magnetic damping changes drastically. You have a high damping in case of high SOC material and a low damping in case of a low SOC material. That's quite expected because you have a higher spin orbit coupling. But then if you see, despite tungsten tantalum being not so far in terms of SOC strengths maybe, but still the magnetic damping values are quite wildly away. So that raised one question. And second was that if you look at the spin chemical potential for copper, which is a low SOC potential, SOC material, we had a much larger interfacial spin chemical potential compared to a high SOC material like tungsten. So to address this again, we employed electronic structure measurements. We did a hard X-ray dichroic photoemission measurement, and what we saw was that when you have tantalum or a tungsten underlayer, the dichroic asymmetries are kind of smaller compared to in case of copper. So it's very important to think here. So we have the same ferromagnetic material, but just because we are bringing in a different kind of non-magnetic layer underneath it, the spin polarized structure near the Fermi level is getting changed. So it's not that we are doing anything, and structurally these material looks similar. So it's the electronic structure interaction between the underlayer and the ferromagnetic layer that is affecting the spin polarized structure of the ferromagnetic layer at the interface. So this was the first finding which we found. I mean, I don't think any of such findings have been done before. But this was very interesting because with this now we can explain what the other groups have seen in terms of spin dynamics effect. So we could clearly see that when you have a higher once you have higher, a system, when you bring a ferromagnet which has got high low spin polarization, kind of low spin splitting at the Fermi level with respect to non-magnet, which is in the case of tungsten tantalum, you expect to have a lower spin chemical potential because you have lower you are driving lower spin polarization current into one to other. So that's what is happening here. But in case of copper, of course, you have much higher split, so you get much higher spin chemical potential. That was quite clear from these measurements. I think this mic is not working. I mean, it's better to give the hand mic. So it's fine. So, but the next question was that what happens here? So you see tungsten and tantalum, though they are very close, as I was saying, have got very wildly differing magnetic damping. Rather, tantalum is closer to copper in terms of magnetic damping. So to address this, we again had a look at the electronic structure carefully. And what we find is that now this is a spin integrated, no, it's not a circular dichroic measurement, it's a total photoemission measurement. And what we find is that this tailing part, which I was telling you gives you information of near Fermi level occupation states or phase space near Fermi level, we can see in case of tungsten you have more tailing compared to in case of copper tantalum. What it indirectly tells you is that you have more scattering phase space in case of tungsten than in case of tantalum. So it's just not trivial that you have a higher SOC material which influences your spin polarization in a direction, in a way that you get higher damping. It's too many crazy things running around. Huh? So the point is you have to integrate, you have to have a full integrated picture of this thing. So in case of cobalt, iron, tungsten, you can think something like this is happening. You have more unoccupied space to scatter into, but not in case of tantalum. And when you put this combined picture, now you can understand that though tungsten and tantalum are high SOC material, both of them, but just because you have a higher scattering phase space, you can get magnetic damping differences. So clearly, while designing such a structure, we have to take care of various aspects of electronic structure correlation of the underlayer with respect to the ferromagnetic layer. I think with this, I would like to thank the organizers once again, and these are the team which actually worked very hard for this studies. Yeah, thank you, Mohit.
Thanks for the nice talk, Govinda. So now it is open for questions. Yes.
So what is the role of interfacial roughness and then defects that exist in your sample and your damping parameters?
Yeah. So of course these all affect. Let me answer you in this way because there are two aspects to scattering. One is of course the physical scattering, and here I was talking about how the electronic phase space is scattering phase space is getting altered. In these systems, we have very well characterized physically all this system, and as we vary the physical system in terms of underlayer or in terms of thickness, our interfacial roughness and defect densities remained, I would not say constant, but of the order magnitude constant.
So do you think like these things would influence your device?
Yeah, this will of course influence the device, and this is well known. So this was exactly the point. In terms of interface roughness, in terms of defects, you expect this external scatterings to increase, and that's well known. But what we have shown here is that if you keep that constant, then just because of electronic structure modulation, you can get the magnetic scattering device performance different. So you have to be careful about the material that you choose itself, just because they are electronic structure induced effects. Yeah.
Thanks for this nice talk. So my question is, you have take the XMCD for your both the measurement that you have shown. Have you quantified the value of orbital to spin moment ratio, and because you try to correlate with it, so how is it behaving with the spin moment that you are telling about, the spin pumping effect and that?
So firstly, we didn't do XMCD measurement. XMCD measurement is different than dichroic Fourier emission measurement.
So you just did
We did XPS actually.
XPS only,
We
not
did
the XMCD.
no, but that's what I was trying to say. The advantage of XPS over XMCD here is that we are, of course, XPS is the best thing to measure the electronic structure. So we measure the electronic structure. On top of it, we are able to pick the signature of spin effects. I mean, at the Fermi level, because there is an exchange interaction between the spin polarized valence band and with the core level. So in the final state of the photo emission, you get the picture of it. That's what I was trying to say. That when you
But in your second measurement, I think there was an green color graph. Is it okay? Maybe
yes. I will show you. That's the dichroic asymmetry that we measure.
Yeah.
So
So
it looks just like XMCD, but it is not XMCD. So everywhere we have this. Like for example here, it's dichroic asymmetry. So it's the dichroic asymmetry. It's not the. So that's what I was trying to say. It gives you as a final state measurement, it gives you let me say in that with the order of strength of spin polarization. It's not really that I can quantify it. It's very difficult. It's a final state effect. So then I have to take care of many other things.
But very interesting work.
Yeah. Thank you.
Any more questions?
I think Debjanidhi had one.
But I have to talk. But anyway, this COFEB, is it in crystalline state or is it in amorphous? Because 5 nanometer just.
Yeah. So this one, what the coffee bee here is, it's a polycrystalline thing. It's not a. Yeah. In fact, for device structures, mostly people are working with polycrystalline and to some extent amorphous as well.
Yeah.
So it's.
Yeah, that's why maybe I was thinking that lattice parameter of tantalum and W and Cu, all of them are not very close, right?
No.
So that's why that lattice parameter mismatch, that does not affect your.
Absolutely, you got it right. So structurally they were, that's why kind of similar. That's why I wanted to highlight this point, that despite structurally being so close and including the roughness and all that he was talking about, we still have a change in the ferromagnetic layer, which shows that is the interaction of the proximity electronic structure influence of the underlayer onto the ferromagnetic layer, which needs to be considered.
Very nice.
What thickness means DESY can measure?
Sorry, I couldn't hear you.
What thickness it can measure this DESY?
DSY?
Usually XPS measure till 10 nanometer.
Acha, okay. So I think we have an extremely, I will call it like India's photo emission father here sitting right behind you, but still I will take this I will take this risk of answering him still. So what we did, you're right. So photo emission is surface sensitive. That's one. So there are two things like information depth, and so when you do a calculation, you get much larger information depth than what you expect just by calculating inelastic mean free path. And we have seen it for several systems. So when you use a lap source, of course, the inelastic mean free path is also very small, and that's what I tried to draw somewhere. Oh, I should have it somewhere. Here. So you are right. Like when you have got this, lap sources, you normally typically have a much smaller inelastic mean free path. But as the moment you have a harder X-ray, you can think hard X-rays like this. So why something does not give you an information, because that itself can create more excitations. In other words, that itself gets absorbed. The energy of the excitation gets absorbed in the material, and you don't get the real information out, right? But with hard X-rays, it sits in, and when I say hard X-rays, it's a spot between 2 keV to say let's something like 7 keV or 8 keV max. This is a sweet spot where you are firstly not able to excite many of the excitations. It's very interesting actually, right? So if you don't have many excitations, if your energy levels are this small, it will not excite, right? It has to really match. That's quantum mechanics, right? So that's one. And I've been a bit liberal at saying this, but just take my word. Secondly, when you do a photo emission, it's a product of photoionization cross-section with how deep you can measure. So this combination sits very well between 2 to 8 keV. And that is inelastic mean free path, but though it counts around 10 nanometer, depends upon what material you are doing, you are right. But it's like a Gaussian tail, right? So you still get some information from little deeper things, and we have seen it in all materials. So it's not restricted to 10, you might get even deeper, depending on material. Yes, you get some more information, yeah.
Any more? Okay, if not, then just like, oh, okay, yeah.
Hello sir, in same material like a platinum or tungsten, if we tune the thickness of the non-magnetic material, then what will be the effect of these results on the like alpha and mu s?
Very good question. So there are two aspects. I was talking in terms of aspect of electronic structure effect on the ferromagnetic layer, right? Now, in that aspect, I don't expect much to happen. Because here, what we are trying to say that the electronic wave structure, so my guess is that when you have a non-magnetic layer, it has got its own electronic wave function that is, going into the vacuum as well. It's not restricted in the layer itself. That itself creates some effects on the electronic structure of the ferromagnetic layer at the interface, right? That changes the spin polarization, all spin dynamics effect. So that does not change if you make a thicker layer or a thinner layer. This is my guess, until unless you get to a monolayer limit. Right? But if you say if it's a 10 monolayer thing or something like that, it shouldn't make a difference 10 and 100 monolayer thing. But from the other perspective, in terms of, I was talking about spin pumping. So, you have a angular momentum which, spin angular momentum which goes from ferromagnetic layer into non-magnetic layer. Now, if the thickness of the non-magnetic layer is not good enough, then this spin angular momentum can go to the next wall of the non-magnetic layer and retro-reflect and come back into the ferromagnetic layer, increasing the magnetic damping. So therefore, you need this is a different effect, but it will also cause a change in the overall spin dynamics or the spin transport behavior of the device itself. So that's why you need certain, and all the measurements that we did were, of course, with pretty thick, 10 nanometer kind of non-magnetic layer. So we avoided those kind of effects. So yeah, so that way it can affect.
Okay, thank you. One more question. We are discussing about interface like non-magnetic and ferromagnetic. Do you think is there any role of the Raspberry spin orbit coupling in this measurement?
Oh, very, very interesting. So well, again, when you talk about Rajba spin orbit, it depends upon what system you are putting there. So right, we have not worked with any Rajba system, so to say here. So all the systems that we worked here are none of them had although bismuth can have, but we never worked with bismuth. But indeed, people know that they bring with Rajba systems as an underlayer and use, because Rajba system has got this added large SOC, right? And this is well studied in like Rajba systems. So of course they do affect, but that's again a different structure, a different kind of electronic structure, additional effect that you will get. Yeah.
Okay, thank you.
Yeah.
Let us thank the speaker.
Thank you.